The final lesson in this unit has to do with improper integrals. Now, improper integrals involve finding values of an integral where a limit is infinite, so something like the integral from 1 to infinity of 1 over x squared dx, or something where there's a discontinuity. So, for example, you do not yet know how to find the integral from -1 to 3 of 1 over x squared, because technically speaking, the fundamental theorem of calculus only applies if this function is continuous on the interval from -1 to 3, and since 1 over x squared is undefined at x equals 0, you do not know how to do that yet. Alright, let's start with how might you begin to find the integral from 1 to infinity of 1 over x squared dx. So you know how to find integrals when the bounds are numbers. So what we can do is find the integral from 1 to a number b instead. Let's just make that x to the -2. And then we can take a limit as b goes to infinity. And that's going to give us the value of that integral. So now we have the limit as b goes to infinity. Alright, the antiderivative of x to the -2 is x to the -1 divided by -1, evaluated from 1 to b. So we have the limit as b goes to infinity of -1 over b minus 1 over -1. So that limit will equal 1. So what that tells us is that the integral from 1 to infinity, 1 over x squared dx, is equal to 1. And what that means is that the area under the curve y equals 1 over x squared on the interval 1 to infinity is 1. So even though you plug in infinitely large values, this thing gets small enough that this area, the value of that area is actually 1. Okay, now here's how you find all sorts of improper integrals. So if your upper bound is infinite, you use some number b and find a limit as b goes to infinity. If your lower bound is -infinity, you do something similar. So you let a, or b, in this case it doesn't really matter, but let some variable go to -infinity and replace the -infinity by that variable. And if you have the area under a curve between -infinity and +infinity, you break that integral up for some value in the middle, and you can use whatever c you want. An easy choice is often c equals 0. And you can find this integral and that integral using the previous techniques. So evaluate the integral from 0 to infinity of e to the -2x. So that will be the same thing as the limit as b goes to infinity, and the integral from 0 to b, e to the -2x dx. So the limit as b goes to infinity. Now an antiderivative of e to the -2x is -1/2 e to the -2x, 0 to b. Now first plug in b, the limit as b goes to infinity, -1/2 e to the -2b plus 1/2 e to the 0. E to the 0 is 1. And this becomes the limit as b goes to infinity, -1 over 2 e to the 2b plus 1/2. And as b goes to infinity, this part goes to 0. So we have 0 plus 1/2 is 1/2. Alright, next, find the integral from 0 to infinity of 1 over x squared plus 1. So start the same way. Find the limit as b goes to infinity of the integral from 0 to b, 1 over x squared plus 1 dx. And the antiderivative, or an antiderivative of 1 over x squared plus 1 is arctan x evaluated from 0 to b. So you have the limit as b goes to infinity of arctan b minus arctan 0. Arctan of 0 is 0, so all you're asked to find now is the limit as b goes to infinity of arctan b. And tangent has vertical asymptotes at negative pi halves and pi halves. So when you talk about arctan, you're looking at just this one oscillation of the tangent graph. Arctan you get by switching the x's and y's, or reflecting that over the line y equals x. So here's what the graph of arctan looks like. So from that picture you can see that as b goes to infinity, arctan of b approaches pi halves. So this limit is actually pi halves. Had I had a limit as b went to negative infinity, the value of arctan b would have been negative pi halves. So sometimes these values of areas under curves given an infinite interval are going to actually be infinite, and here is a pretty important example. So we're going to find the integral from 1 to infinity of 1 over x dx. So start the same way. We have the limit as b goes to infinity, 1 to b, 1 over x dx. An antiderivative of 1 over x is ln x. So ln absolute value x from 1 to b. So the limit as b goes to infinity of ln b minus ln 1, and because b is going to positive infinity, I can drop those absolute value bars, and this is actually going to be infinite. Alright, suppose we have the integral from negative infinity to 0 of x e to the x. So first we'll find the limit as b goes to negative infinity, integral from b to 0 x e to the x dx, which we can say is the same thing as the limit of b going to infinity, the integral from negative b to 0 of x e to the x dx. Now the tricky thing is you have to actually integrate x e to the x dx, which you have to use integration by parts to do. So just on the side, let's work that out. X e to the x dx. So that will equal uv minus integral v du. So if u is equal to x, du is equal to dx. And if dv is equal to e to the x dx, v is equal to e to the x. So the integral of x e to the x is equal to x e to the x minus the integral of e to the x dx. So x e to the x minus e to the x. And so now we're going to use that antiderivative. So we have the limit as b goes to infinity of x e to the x minus e to the x evaluated from negative b to 0. Now we plug in our values, and we have first you plug in 0, so you have the limit as b goes to infinity of 0 minus 1 minus negative b e to the negative b minus e to the negative b. So that's the limit as b goes to infinity of negative 1 plus b over e to the b plus 1 over e to the b. And now we can limit each term individually. So the limit as b goes to infinity of negative 1 is going to simply be negative 1 plus the limit as b goes to infinity of b over e to the b. Now this last thing, as b goes to infinity, that's going to go to 0 because you have 1 divided by a large number. To evaluate this middle limit, we have to use L'Hopital's rule. So the limit as b goes to infinity of e of b over e to the b will equal the limit as b goes to infinity of 1 over e to the b, which will be 0. So negative 1 plus 0 will give us the area underneath this curve is equal to negative 1. And that means that the curve is overall below the x-axis. Alright, next let's find a value of an integral where both the bounds are infinite. So first, let's break this up into the integral from minus infinity to 0, 1 over 1 plus x squared dx, plus the integral from 0 to infinity, 1 over 1 plus x squared dx. So first, we'll find the limit as b goes to minus infinity, the integral b to 0, 1 over 1 plus x squared dx, plus the limit as b goes to positive infinity, 0 to b, 1 over 1 plus x squared. And just a note, you don't have to use 0. You can use whatever number you want. You should get the same answer either way, but 0 is just a nice, easy number. So now when we antidifferentiate 1 over 1 plus x squared, in both cases, same function, we get arctan. So limit b goes to minus infinity, arctan x evaluated from 0 to b, plus the limit as b goes to positive infinity, arctan x evaluated from 0 to b. So we have the limit as b goes to minus infinity of arctan 0 minus arctan b, plus the limit as b goes to positive infinity, arctan b minus arctan 0. Now arctan of 0 is 0, so we have the limit as b goes to minus infinity of negative arctan b, plus the limit as b goes to positive infinity, arctan b. And as we discussed in the previous example, arctan's graph looks like this with asymptotes at positive pi halves and negative pi halves. So as b goes to minus infinity, arctan b goes to negative pi halves. So there we have negative pi over 2, plus, and as b goes to infinity, arctan b heads off towards pi halves, so plus pi halves, and this gives us pi halves plus pi halves, which is equal to pi. Alright, next let's determine for what values of p is this integral convergent. So when does it equal a number? So we already, in an earlier example, examined the case from 1 to infinity 1 over x dx. We know that this diverges. So we are going to start by assuming that p is not equal to 1 in that case. So we'll find the limit as some b goes to infinity, integral from 1 to b, and we'll just make that, let's make that x to the negative p dx. So you have the limit as b goes to infinity. Now the antiderivative of x to the negative p is x to the negative p plus 1 divided by negative p plus 1, evaluated from 1 to b. So the limit as b goes to infinity of b to the power of negative p plus 1, I'm just going to make that 1 minus p, minus now 1 to any power, any finite power is 1, so 1 over 1 minus p. And I would like to just factor out the 1 minus p, so I have the limit as b goes to infinity 1 over 1 minus p times b to the negative p plus 1 minus 1. So now we have the limit as b goes to infinity 1 over 1 minus p. Now b to the negative p plus 1 is the same thing as 1 over b to the power of p minus 1, and then minus 1. Now, if your p is bigger than 1, then p minus 1 is bigger than 0. So as b goes to infinity, b is going to be raised to a positive power, so b to the p minus 1 is also going to go to infinity, meaning 1 over b to the p minus 1 will go to 0. If p is less than 1, then p minus 1 will be less than 0, and this term will go to infinity. 1 over b to the p minus 1 will go to infinity. So this integral is convergent if p is bigger than 1. So if you have 1 over x to the 3 halves, 3 halves is bigger than 1, the integral is going to converge. And it will converge too because this term, assuming that this is true, that term is going to go to 0. And your integral will be the same thing as negative 1 over 1 minus p, which is the same thing as 1 over p minus 1. And that's assuming that p is greater than 1. Now, we can also use a similar reasoning to evaluate integrals where there is a discontinuity inside of the interval or on the end of the interval itself. So if a function f is continuous from a to b and has an infinite discontinuity at b, so you have your interval from a to b, you want to come at b from this side, so that's why the c is going to b from the left, and you can find this integral instead and then take the limit. And similarly, if the function f of x is discontinuous at a, you want to come at a from the right, so that's why we have c going to a plus. And if the discontinuity is in the middle, so somewhere between a and b, you can break it up into two integrals, one from a to c, one from c to b, where c is the value where the discontinuity occurs, and find each of those individually. Now, one way you can save yourself a little bit of work is if either of those are infinite, the whole thing is going to diverge. So you could just say find this one, say that one is infinity, and therefore your entire thing diverges no matter what the value of the other one is. So first we have the integral from 0 to 8 of dx over the cube root of x. So here the problem is 0. 1 over cube root of x is undefined at 0. So we find the limit as b goes to 0 from the right. Integral from b to 8, and we'll have x to the negative 1/3 dx. So we have the limit as b goes to 0 plus. Now the antiderivative of x to the negative 1/3 is x to the negative 2/3 times 3 halves from b to 8. So you have the limit as b goes to 0 from the right. 3 halves times 8 to the 2/3 power minus 3 halves times b to the 2/3 power. So this will just go to 0. And then 8 to the 2/3 power. So we have 3 over 2. So 8 to the 2/3 power is the third root of 8 squared. So the third root of 8 is 2. 2 squared is 4. We have 3 halves times 4, which is 6. Alright. The integral from 2 to 5 of 1 over the root of x minus 2. Once again, here the problem is at the lower bound at 2. So we find the limit as b goes to 2 from the right, integral from b to 5, and I'm just going to write that as x minus 2 to the power of negative 1/2. So limit as b goes to 2 plus Now an antiderivative of x minus 2 to the negative 1/2 is x minus 2 to the positive 1/2, negative 1/2 plus 1, coefficient of 2, evaluated from b to 5. So limit b goes to 2 plus 2 root 5 minus 2 minus 2 root b minus 2. So as b goes to 2, this term goes to 0. So we end up with just 2 root 3. Determine whether the integral from 0 to pi halves of secant x dx converges or diverges. So secant of x, the graph of it looks like that, at least between negative pi halves and pi halves. So there's positive pi halves, here's negative pi halves. Remember, it's 1 over cosine. So the problem point here is pi halves, discontinuous there. So we'll find the limit as b goes to pi halves from the left, integral from 0 to b secant x dx. Now the antiderivative of secant is a pretty tricky thing to derive, but we've used it quite a bit. It's ln absolute value secant x plus tan x, evaluated from 0 to b. So you have the limit as b goes to infinity, or b goes to, not infinity, pi over 2 from the left, ln absolute value secant of b plus tan b minus ln of, when you plug in 0, secant of 0 is 1, tangent of 0 is 0, so minus ln of 1. And ln of 1 is 0. Now, as b goes to pi halves from the left, secant of b is going to go to infinity. Tangent of b is also going to go to infinity. So we have ln of a large number, which means that this actually diverges. This is infinity. So this integral is infinite, it diverges. Converges is equal to a finite number. Diverges would mean it goes to infinity. Alright, evaluate the integral from 0 to 3 of dx over x minus 1. So here the problem is that this function, 1 over x minus 1, is not defined at 1. So we have to break this into two integrals, one from 0 to 1, 1 over x minus 1 dx, plus 1 to 3, 1 over x minus 1 dx. And let's just work on this first one. So for the first one, 0 to 1, 1 over x minus 1 dx, the problem's at 1. So we'll find the limit as b goes to 1 from the left, 0 to b 1 over x minus 1 dx. So that's the limit as b goes to 1 from the left, ln absolute value x minus 1, evaluated from 0 to b. Maybe a couple problems here. The limit b goes to 1 from the left, ln of b minus 1 minus ln of negative 1. In absolute value bars, so that'll be ln of 1. But the problem is this thing right there. So as b goes to 1 from the left, b minus 1 is going to go to 0. And if you remember what ln's graph looks like, as you plug in numbers closer to 0 into the log, this expression goes to minus infinity. So there ain't no fixing minus infinity, so this expression, or this integral, diverges. And you do not have to worry about what the value of the second component is, because since the first one is infinite, the whole thing is going to diverge. If this first integral had equaled a finite value, you would have to also find the second, and the area under the curve between 0 and 3 would have been the sum of those two answers. Now, there's one more theorem that's important to know and pretty intuitively obvious. So suppose you have functions with f of x greater than g of x, which are bigger than 0. So here's f of x. Here's g of x. Okay? And we care about some number a off to infinity over there. Now, if the integral from a to infinity of f of x is convergent, so is the integral from a to infinity of g of x, which should make sense, right? Because if the bigger one converges, then so does the smaller, right? That should make sense. And similarly, if g of x is divergent, then so is f of x. And the reason is g of x is the littler one, so if the little one diverges, so does the bigger. So we're going to use that in this next example. In this next example, we are going to find the volume of an infinite solid of revolution and the surface area of the same thing. So we have 1 over x for x greater than 1 rotated about the x-axis. So there is my 1 over x that I care about. From 1 to infinity, I'm going to rotate this about the x-axis. So my cross sections are going to be circles. The area of my circle will be pi r squared, and in this case my r is equal to 1 over x. So the area of my cross section is pi times 1 over x squared, or pi times 1 over x squared. Now to find the volume, I will add them all up. So pi times the integral from 1 to infinity, 1 over x squared dx, or pi times the limit as b goes to infinity, 1 to b, x to the negative 2 dx, limit b goes to infinity. So the antiderivative of x to the negative 2 is negative 1 x to the negative 1. Now plug everything in. We have pi times the limit as b goes to infinity, negative 1 over b plus 1, and 1 over b goes to 0, so the volume of this horn is pi. Next, let's find the surface area. So the equation for surface area was the integral from a to b, 2 pi r times the root of 1 plus y prime squared dx. And think about this as r is the radius, that this 2 pi r finds the circumference of a little slice, and this expression finds the length of that slice. So, first of all, y prime is equal to negative 1 x to the negative 2, so y prime squared is 1 over x to the 4th. So my surface area will be equal to an integral from 1 to infinity, 2 pi. Now the radius, so the distance from your axis of rotation up to your curve, will be 1 over x, times the root of 1 plus 1 over x to the 4th dx. And since my x's are positive, this thing is bigger than 1. So this expression is bigger than or equal to 2 pi times the integral from 1 to infinity, 1 over x dx. And we found out earlier on that this is divergent. And so using that comparison theorem, the integral from 1 to infinity of 1 over x dx is the smaller integral, and it diverges. So the original one does too. So this surface area is actually infinite, not a finite number. This is a really interesting solid shape thing. So it has finite volume, but infinite surface area, which should be a little bit odd, but that's why. So that's what it is. What it is. Infinity does strange things. Strange things happen at infinity. So